In early calculus, evaluating a limit usually means relying on a familiar set of algebraic operations, factoring, canceling, or simply plugging in a number. But when mathematical sequences grow more complex, those direct computational methods hit a wall. Take a sequence like the nth root of n. As n approaches infinity, the base grows endlessly, while the exponent shrinks toward zero. This creates an indeterminate form, rendering basic algebra useless. Recursive sequences pose a different problem. Consider the sequence defined by x sub n plus 1 equals the square root of 2x sub n. Because each term relies entirely on the value of the previous one, attempting to evaluate the limit directly traps you in a loop of circular logic. Then there are oscillating sequences, like the sine of n. Because the output constantly waves between positive and negative values without ever settling, standard limit rules cannot apply. To deal with these, we have to move past elementary calculus and enter real analysis. Here, we stop asking how to calculate the exact numerical value and start asking what structural properties govern the sequence itself. We are going to master 3 indirect structural tools: the clamp, the ceiling, and the split, to evaluate the limits that algebra cannot solve. The first tool is the sandwich theorem, which allows us to evaluate a sequence by trapping it between 2 external bounds that we already understand. The second is the monotone convergence theorem. This establishes that if a sequence moves in only one direction and hits a strict numerical barrier, a limit is mathematically guaranteed to exist. Finally, we use subsequence analysis. By breaking a sequence into smaller, independent parts, we prove divergence through internal contradiction. These 3 methods allow us to verify the existence of a limit, even when direct calculations remain impossible. Instead of chasing individual terms to infinity, we will construct logic constraints that leave a sequence no choice but to reveal its exact destination. The logic of the sandwich theorem relies on strict bounds. If you have a complex sequence squeezed exactly between a higher sequence and a lower sequence, and both outer sequences converge to the exact same point, the complex middle sequence is physically squeezed there. Let's apply this to a specific challenge. We need to rigorously prove that the limit of r to the power of 1 over n equals 1 for any constant r greater than or equal to 1. We define xn as r to the power of 1 over n minus 1, shown by white dots. If they converge to 0, the original limit is 1. Because r is at least 1, its root is 1 or greater. Thus, xn never drops below 0, establishing an absolute lower bound. To find the ceiling, we look at the original definition, r equals 1 plus xn to the power of n. By applying the standard binomial inequality, we know that 1 plus xn to the n is greater than or equal to 1 plus nxn. Isolating xn yields xn is less than or equal to r minus 1 over n, mapped as this descending red curve. As n grows to infinity, dividing the constant r minus 1 by n means this upper bound goes to 0, pinching the white sequence against the 0 floor, permanently trapping it. By utilizing the sandwich theorem, we substitute one difficult calculation for 2 accessible bounds. Let's return to the recursive sequence xn plus 1 equals the square root of 2xn, starting with x1 equals the square root of 2. To find its limit algebraically, we first need absolute mathematical proof that the limit actually exists. This is where the monotone convergence theorem applies. The theorem states that any sequence moving in a single direction, being monotone, that is also capped by a strict numerical boundary must converge. This handwritten proof outlines the initial step. By using mathematical induction, we establish the sequence is strictly bounded above. Every term in the sequence will remain strictly less than 2. Next, establish direction. Each term x sub n plus 1 is strictly greater than the previous x sub n. On this number line, points march steadily right. Because the sequence constantly increases but cannot pass the barrier at 2, it converges to a known limit, L. Now that we know L exists as a finite number, the recursive loop breaks. We can take the limit of both sides of our original equation, leaving us with L equals the square root of 2L. Squaring both sides to eliminate the root yields L squared equals 2L. Solving this quadratic equation yields two possible limits, 0 and 2. Since our sequence starts at square root 2 and is strictly increasing, L equals 0 is impossible. The limit evaluates to 2. By utilizing this ceiling property to establish convergence first, we transform an infinitely recurring process into a standard, solvable equation. What happens when a sequence doesn't settle? Take x sub n equals sine n. Convergence requires that every possible infinite subsequence drawn from the main sequence arrives at the exact same limit. Therefore, to definitively prove a sequence diverges, we only need to extract two subsequences that approach different destinations. This graph plots the sine wave. Notice the upper shaded regions, in, greater than 1/2. Being wider than 1, each contains at least one integer, forming subsequence nk. This forces the limit to 1/2 or higher. Conversely, lower regions, jn, drop below -1/2. By the same logic, we define a second subsequence, mk, targeting the integers inside these troughs. This subsequence forces its limit to be -1/2 or less. This creates an immediate contradiction. A single sequence cannot possess a limit that is simultaneously greater than 1/2 and less than -1/2. Subsequence analysis identifies divergence by isolating these conflicting internal properties. Side by side, we see the topological architecture of how we handle infinity. The sandwich theorem locks a sequence into place by leveraging the algebraic bounds of its neighbors. Monotone convergence handles self-referential systems by using strict direction and rigid boundaries to guarantee a destination. And subsequence analysis isolates the internal contradictions of non-convergent, oscillating sequences. These methods exist beyond solving textbook exercises. They form the structural foundation of higher analysis, directly supporting major results like the Bolzano-Weierstrass theorem. Real analysis requires a shift in perspective. It is the careful study of exactly how mathematical limits are constructed, constrained, and rigorously justified. When direct algebra fails, you build the underlying logic. If you rigorously bound a sequence and prove its direction, you control its limit. If the internal components of a sequence contradict each other, you prove the system is broken. By mastering these three tools, we establish the rigorous framework necessary to verify the destination of a sequence, regardless of its initial complexity.